Good morning, everyone. My name is Yvan Petillot. I'm a professor of robotics at Erasmus University, and I'm the director of the ORCA Hub. So this webinar is to update everyone on two things. First, an update on what we've done in the Hub to date. And secondly, an update on the new funding that we've been given to push forward the results we've achieved to date in the following year. So I will give you an overview of the ORCA Hub and the result to date in the first 20 minutes. And then each of the challenge leads on the new funding will give you a presentation on their respective challenges. And finally, David Wevel, who is our ORCA business executive, will tell us how to engage with us in the future. So ORCA is one of the robotics hub for extreme environment funded by EPSRC under the ICF, and we've received 18.5 million of funding. It involves 5 core institutes: Heriot-Watt, Edinburgh, Liverpool, Oxford, and Imperial College. And we've had included 8 new partners through Partnership Research Fund. So the vision of the hub, the original vision, was really to support the long-term offshore industry vision for autonomous offshore energy fields. And what we've been trying to do is to map the key competencies and development within robotics to achieve that. And we had 4 key work packages: mapping, surveying, and inspection, which is planning, control, and manipulation, intelligent robot interaction, and asset certification, as well as robot certification. Over the last 3 years, we've really reached out to industry, and we've had a number of funded projects with industry to try to push the results of the research into the industry and promote innovation. So what I'm going to do now is go to a quick whiz round of what we've achieved to date in the 4 work packages that we have. So the first work package was about mapping, surveying, and inspection. And we have looked at the 3 domains. So the first domain is Septi. And in this domain, we have created a new mobile platform that can be integrated into any underwater vehicle, which includes a stereo camera system, an acoustic DVL, and gyroscope, and enables us to navigate around structure in poor visibility and build 3D maps of the structure. So this is an example of the vehicle working in Blythe, where the visibility was very poor. We have done similar things in the air and land environment. So this is work led by Imperial College and Oxford University. So they have developed again a payload that can be mounted on any vehicle really, that enables them to do effective mapping of the environment. So this is an example in Oxford where a ground vehicle is mapping the area, but also an example here where it's an aerial vehicle mapping an area outside the campus. And with this, we can build, sorry, I'm trying to find really nice models of the environment. And as I said, this can be applied in various settings. So this is a ground robot equipped with the same payload. There's also been work done with quadruped robots and around the LiDAR-based payload, where we can build, again, 3D maps of the environment. So it's an example of the system working outside Oxford in Oxford College, where you can see the quality of the maps that are built in real time. I must add that it's not just mapping, we're also doing localization at the same time. So it's a full SLAM system, both in the air, land, and sea, where we can also localize the vehicle very precisely in the environment. So the mapping and sensing had a second component to it, which was looking at building new sensors for helping the asset certification. So one of the sensors that was built by Imperial College is an NDE sensor based on EMATS, which has since been commercialized as part of a startup called Robotics. And this sensor has been deployed on our land, air, and underwater robots for corrosion monitoring. The second type of sensors was more in looking at IoT. So the University of Edinburgh has developed a multi-sensor payload, which is very small form factor, very low power, and that can be deployed in any environment and measures basic parameters such as movement, temperature, etc. And this payload has a multi-communication framework, so you can connect to it through Wi-Fi, Zigbee, serial, etc. And we've deployed this on offshore wind farms, underwater water, and one of the Stream A challenges to actually demonstrate that at sea. So moving on to control and manipulation. So we have worked on not just about moving around, but also being able to plan the motion in complex environments. So you see on the video in the right that the vehicle is moving and will identify that the area is blocked, and it can automatically remap and go to the right of the image to find the right solution. It can also adapt its gate to the type of environment. So if there's obstacles, the gate is autonomously adapted to make sure that the obstacles are tackled safely. On the planning and manipulation, we've also been looking at skill-based share control. And what we mean by that is knowing when the operator needs to take control of the manipulation. So there's an example here. So this is an example in the construction domain with Costain, where we are looking at cleaning and painting some surfaces. Here it's an element where we are cleaning a surface, and you can see that the operator is using the robot through an interface, but he's got a much better control of what's going on. He's not controlling the contact, but just the trajectory on the contact. So that's enabled to assist teleoperation when executing complex motion by integrating advanced control in the system. Similarly, we've been working in control system when we are doing interactions with mobile platforms, or when we are acting from mobile platform to the world that is fixed. And we've developed some interesting control algorithms that enabled us to follow a trajectory on a fixed pipe, for instance, top left, from a mobile platform. This is very important for all the applications underwater, where a lot of the manipulation will be done from a floating platform. More work's been done on the deployment of the sensors from mobile manipulators. So you can see here an example in simulation where we are first scanning the environment using a sensor, and the robot is designed to scan the environment. And once the environment has been scanned, oops, sorry, it went up. Once the environment is scanned, we can actually operate properly with the robot. You can see the robot's doing the same thing here. And after the scanning, it will perform the full scan of the environment, which is performed here. So this can be done from a platform that is static, but we've now extended it from a platform that is also mobile. On the aerial side, we have done lots of development. You'll see more videos later during the challenge demonstrations. But the group in Imperial College has developed techniques to do autonomous perching, which enables you to deploy a sensor and move actually the aerial vehicle around the structures to perform the same type of monitoring we're doing with the land and the underwater robot. So that enables you to access places which are really hard to reach, such as turbine blades and very high structures. So I'm moving on now to the third part of the work package 3, which was looking at interactions. So it's great to have robots that work autonomously, but it's equally important to make sure that the robot user understands what the robot's doing. So on that front, we have developed an interface called Miriam, which enables people to, it's effectively a chatbot. We call it a chatbot. Enables people to interrogate the robot, but also ask the robot to execute specific tasks and ask for feedback during the mission. So in this case, you can see a robot that is tasked to do an inspection. So this is a Husky robot. And while the robot is operating, we can ask questions to the robot about the mission in natural language. And the type of question you can ask is, when is the mission going to be complete? What are you doing exactly in the mission? Which task are you tackling? And the robot can also report problems and faults, and then the human can retask the robot. This works in a single robot environment as well as multiple robot environment. And on the work package 4, we've been working on verification and simulation. So we've done a lot of work on robot and assets self-certification, written a number of white papers, participated to standards, and also worked on validation of operational envelopes of robots, for instance, on flying vehicles. So in the top right, you can see that you've got a complex structure with waves and wind interaction with the structure, and we can, using simulation, determine where it is safe for the UAV to fly in order to do its mission. We've also worked on asset integrity, so linking the data with the models of, in this case, a wind turbine blade, to assess its viability in the long term. And we're using machine learning to do the classification. So that's just a quick subset of some of the applications we've been working on. There was a lot more when I was looking at this presentation, but I couldn't present everything. So these are snippets. There will be more data on the website very shortly, so you can also contact us if you want to know more details about this. Finally, we've had nine partners projects that were developed as part of the ORCA Hub. I couldn't present them all, so we've decided to give you two examples. One is an underwater communication system, which reaches hundreds of megabits of data rate over about 30 meters. The other one is to demonstrate that the driver is following the rules and that the deep learning algorithm is not encroaching on those rules. So ORCA Phase 2. So this is ORCA Phase 1, and I've looked really at a subset of what we've been doing. So just to summarize ORCA Phase 1, it was really about developing the key technology in mapping, inspection, control, HRI, and certification, so that we could deploy those robots safely in the environment. ORCA Phase 2 is really looking at three core scientific development, something around shared autonomy, because we realized through the project that the industry is not quite ready for full autonomy. So we really need to develop techniques that enable the user to be situated, but also to take control from the autonomous systems when needed. And so we provide autonomy functions which are of value for the industry, but we don't target full autonomy. We've also realized we need to integrate all the sensors and the robots into a proper cyberphysical system. We look at communication, digital twin, cybersecurity, etc. And finally, we're looking at resilience. So what happens when things go wrong, and how can we make sure that we don't then need to intervene physically, which would probably reduce the business case for the use of robots. And that will be applied across 4 challenges. So one is multi-robot cooperation for inspection in the subsea domain. The second one is aerial inspection of large infrastructure. The third one is robust inspection manipulation on the ground. And finally, the fourth one is the symbiotic system for resilience. And the fifth one is the cyberphysical fabric. So those will be presented to you in a minute. So in terms of what's going to happen over the next year, so the funding of ORCA finishes in March 22. And we have 6 demonstrations of the existing work, which are on the left-hand side. And the new scope, which is stream B, is the 5 challenges I've just described. So this will happen in parallel, and you can engage in both of the streams of work. So if you feel that you want to be part of this, you can contact us, and we'll explain you to do that, how to do that in a minute. So this concludes the kind of first part of the presentation. We now have a number of short 5-minute presentation on the scope, on the new scope of the challenges. And Dr. Sen Wang is in challenge 1, but he couldn't make it today, so I'm going to present that as well. So what we're looking at in this challenge 1 is really to develop a multi-robot remote inspection for the subsea. So at the moment, we have developed a system that can inspect structures using an ROV. And we're working with a number of industrial partners to develop a collaborative system where you have a surface vehicle deploying the ROV around the wind farm, performing the inspection, and then moving to the next wind farm. We're also looking at the data piece. So what do you do with the data? How do you process the data? How do you store the data? How do you extract information from the data? And finally, how do you present that data to the user? So this project is ongoing, and I'm very hopeful that we will have a full demonstration by the end of the project. In terms of what we've achieved to date, we've got all the bits, effectively, component bits. We've got autonomous hardware. We've got this portable payload computer that can be deployed on any ROV to do visual inspection and SLAM. We have done some machine learning work that enabled us to build 3D model, detect specific thing on data, but we also have the full control and navigation stack. Finally, on the operation interface, on the safe operation, we have operators interface, and we have developed a telepresence system that will enable ultimately manipulation as well as inspection. So just to give you an example of this, this is a demo in the tank from a couple of weeks ago, where we have the robot inspecting an unknown structure. So the robot doesn't know the structure is inspecting, and he's driving around the structure autonomously in conditions which are reasonably challenging. And what's quite interesting is, as the robot is moving around the structure, we simulate some faults in the vision system so that the robot cannot see for about 15 seconds. And you can see that there's an automatic recovery of the system where the robot is able to then recover from the failures and keep mapping the whole structure. So this technique is now ready to go, and we're going to test that offshore in the next months. The next step is to integrate it with a surface vehicle to have a remote, completely remote operation deployment from shore. So I'm going to now pass on to Mirko Kovacs from Imperial College, who's going to present Challenge 2.
Thank you very much, Ivan. I hope you hear me okay. So the goal here of the Challenge 2 is to look at new methods of aerial inspection of large infrastructures, in particular on wind farms, so wind turbine blades. Now, drones are already used for wind turbine blade inspection and are basically the de facto standard of flying a drone quickly, taking pictures, identifying damages, and so on. So this is cheaper, faster, and lower risk compared to manual methods of inspecting it. Now, in this challenge, what we focus on is to take the next stage of that, and not just do visual inspection, but to do 3D mapping, so full high-resolution mapping, and also place sensors on the surface to get insights onto the internals of the blade, and like this be able to predict and predict damages, failure modes, and schedule the operations and maintenance aspects of these blades. This can reduce the downtime on the facility and like this save a lot of costs that are associated with the operation of such wind turbines. So we do this not just on the surface, on the outside, but also on the insides. And if you see here on the right side, you see the insides of a turbine blade, where often the data is not existing and often these areas are very constrained, so very hard to access with manual means. The type of sensors that we deploy are twofold. One is the limpet sensor, as you see here on the top picture, which can detect in an IoT type of framework the vibrations and surface features and operations on the surface. So this can also be used as a communication relay, for example, for the drones. The second layer of sensors that we use are the NDE sensors, such as the EMET-based sensors that can detect the corrosion on the surface or the thickness of the material. And this can be integrated into these drones to inspect and monitor the behavior and the surface features. So this is one focus, is the sensor placement in an autonomous way using those drones. The next slide. Then also we work on the mapping aspect of this. And this here is a work led by Oxford University and Imperial College on the high resolution mapping, as you see here in the top picture, where drones use LiDAR and vision in a way of tightly fusing them together with the odometry on the platform to get very high resolution images and be able to change the resolution of the maps to get insights onto the structural performance and structural changes of the blade. At the bottom, you see one of our drones that are very lightweight, so only 100 grams and very small, so palm sized, and have full autonomy. So they can avoid obstacles, fly inside of the wind turbine blade and do internal mapping. So 3D maps of the internals and also place sensors and do surface interaction tasks. Okay, then the next slide, please. And we then also weave this data together into a validation framework for the aerial missions. This includes the interaction with the digital nature of the blade and the way of integrating this to get insights onto the structural and time-dependent performance and change of the blade, but also linking it to the operations and the digitalization of the operations process to optimize the overall scheduling of maintenance processes. On the top right, you also see work that we do here in the challenge 2 on wind robustness. So having flying robots that would fly around the assets, and then we have a simulation framework that allows this to be operated or optimized, so to plan the path in a way that there would be minimal disruption from wind. So overall, in summary, we focus on new methods of 4D sensing. So from structural sensing using 3D mapping to full measurements on the performance and material properties, to fully integrating all this in an autonomous framework to allow this to happen with minimal human intervention and even with remote presence, with those systems being residential on the platform, on the asset, without the humans even having to go there to do it. Thank you.
Thank you very much, Mirko. So we're going to move to challenge 3, which is about robust inspection and manipulation.
Yep. Hi. Thanks, Ivan. I'm Yannis Avotis from the University of Oxford, and I will tell you a little bit more about challenge 3 on robust inspection and manipulation for hazardous environments. I'm leading this challenge together with Professor Setu Vijayakumar from the Edinburgh University as well. Just a slight note there. So in challenge 3, of course, we build on our strengths from phase A, and we further develop work on inspection manipulation. Some of you hopefully have seen our work in person at our demonstrator a couple of years back at the Offshore Energy Catapult in Blyth, and hopefully have an idea about what we've been working towards in the ORCA Phase 1. So there you have seen a bit of our automated inspection work and our initial approach to manipulation. Now in stream B, we're really dialing this up to 11. We're working navigation for real world facility clutter, and we're bringing in quadrupeds with manipulator loads. So we're working towards more inspection and intervention capabilities. And we're going to start with automated monitoring of dials, valves, thermal images, and so on. And then range all the way to non-destructive evaluation scans and anomaly detection. And of course, on the manipulation front, we'll be working towards automatic turning on valves, pressing buttons, and so on. And on the more extreme side of our manipulation vision is to do more extreme intervention like cutting and dismantling for waste handling and decommissioning. So I'm going to give you a little bit more detail on the 4 different strands that we've built for Stream B Challenge 3. So this is a bit more on navigation manipulation with the animal with a manipulator arm. We've been working on facility level multi-floor path planning, and we've been working towards building a temporal semantic map of the environment that what we can integrate with manipulation and locomotion capabilities. In the next slide, you can see here sketches about what we're putting together for local manipulation tasks. So these are tasks that are relevant to energy facilities and so on. The robot can then robustly turn valves, open doors, operate switches, navigate routes with obstacles and doors and so on. And this is in a completely automated fashion. So the robot can either be teleoperated with a really simplistic user interface for the operator to perform these particular skills, or autonomously complete these tasks. Next slide, please. Okay, so in parallel, we're working to further develop our non-destructive evaluation scanning capabilities. We've shown in the past how we can autonomously scan for corrosion, as an example on the videos on the right there. And in the middle, this is more recent work on how we can extend this to even more complex surfaces, more complex geometries. And then, of course, part of our work will be to integrate it with local manipulation on our quadrupeds. Next slide, please. So this is the other end of the manipulation spectrum. We're developing autonomous capabilities for robotized gas cutters. Initially, this will have the form of a gas cutting facility mockup, so with larger manipulator arms. But we're also will be working towards integrating that into mobile manipulators in view to have robotic decommissioning for ship hulls and more large material structures and irregular geometries. And finally, on the next slide, by popular demand, we're expanding our platforms to include the Spot Robot platform from Boston Dynamics. And if you can also play the video on the right, even. So we will be incorporating the inspection payload that we've developed on the Spot robots, and we will extend its capabilities with a learning support anomaly detection pipeline, for example, that can identify corrosion, structural damage, spurious heat signatures around the facility, and log such data precisely, and integrate them to the digital twin representation of the facility. So here's just an example of our ongoing work on multi-floor mapping. This is actually at our lab in Oxford, going through our lab and our office space in the Oxford Robotics Institute. And that concludes the overview of Challenge 3. Thank you very much.
Thank you very much, Yanis. So we're going to move to Challenge 4, which is presented by David Swain.
Thank you, Ivan. So in Challenge 4, building on the successes we had in Stream A, where we created the world's first subsea cable asset management and planning system with in situ inspection with low frequency sonar and robotics. And similarly on the top side, on the surface side of things, we achieved a lot in asset certification for wind turbines, robots and blades. This time, we really want to focus on these barriers, which are stopping companies upscale and fully lock into the value proposition of multi-robot fleets. So we're really focused on how can we give you a transferable toolbox which allows you to address safety, reliability, and resilience. Now, the reason we believe this is very timely is when you look at the growth trajectory in offshore robotics as per the government's 10-point plan, we need to deal with some of these really pragmatic challenges that these off-the-shelf systems need to cope with. So in brief, we're looking at treating these multi-robot systems as part of that digital fabric, and we're focusing on collaboration, cooperation, and cooperation between robots, infrastructure, and people. If you could move on to the next slide, please. Thank you. So for our demonstrator, we have a confined space mission environment. It's going to be an asset integrity mission that is beyond visual line of sight. We will have multi-robot systems, a ground-based Husky and 3 aerial systems deployed. And we're going to use the symbiotic digital architecture that we've developed to coordinate these systems in situ. Our symbiotic digital architecture just now can include in real-time synchronized fashion about 1,000 different embedded systems. So that can be the infrastructure monitoring as well as those in situ robots. And what we're going to use this environment for in engagement with you is we are going to capture some of the safety, reliability, and resilience issues that then we will develop the methodologies for. And we're also going to make the brave decision, or some might think even a foolish one, of handing over control of the mission scenario to our industrial collaborators in order to verify and validate the strategies that we deploy in this environment. If you could move on to the next slide, please. Yep, thank you very much. So our focus here, as I say, is how can we address the issues of the dynamic environment. As we know, these systems themselves have certain thresholds of reliability and lifetime, and we've developed some reliability ontologies that operate in the front end, or edge as it's referred to in these systems. And thanks to the digital architecture we have, we can synchronize these systems and their digital models into one space. And in that one digital environment, we're then going to see how we can mitigate initially the risks around, as I say, safety, compliance, resilience, and reliability. So you can imagine a scenario where we have a forecasted fault in one of the robotic platforms. How can some of the in situ systems help mitigate this, deliver spares, etc. Looking to the future and remembering we want to give you this digital architecture so that your specific requirements, your specific safety case, operational needs, and robotic platforms can be rapidly deployed and scaled with the assistance of this digital enabler. Okay. Is there another slide, Ivan? Yeah, here's, unlike my colleagues, I've not used some of our lovely videos, but there is an excellent link there in the work that we've done with ClearPath, with our deployment at Blythe, where we have demonstrated the bi-directional collaboration with the human in the loop partner, working with the digital environment that represents in real time the field systems. And in that video, you will see how we've started to address the challenges of unplanned threats to the safety case, such as a person unintentionally entering a mission space, or when we have an unknown fault emerge in the system. And what you will see on this video is how we take a lot of complex front-end analysis, but deliver that in a really engaging format for a non-expert to understand. So in the video clip, you will see that we can support a remote digital teardown, so to speak, of each of the individual systems that we've deployed in situ, so that the human can not only collaborate with, but also query and reassure themselves on the, for example, the state of health of the systems in situ. So just as a kind of closing statement here, I imagine, is we want to look at, as I say, safety, reliability, and resilience. And we have an excellent environment, a confined space, asset integrity mission environment, where we're going to be working with your input to develop models and mitigations to the challenges, the barriers that you see in deploying these systems as business as usual solutions in the future. I think that's all of my material, Ivan.
Thank you, David. So we move on to final challenge led by Adam Stokes.
Okay, thanks, Ivan. So this last challenge is an interesting one. So what we've had so far is 4 different use cases that represent different challenges within the ORCA Hub. This last one is a cross-cutting challenge that goes across all 4 of the things that you've seen previously. And the idea here is that we're looking at this so-called cyber-physical fabric. So what does that mean? Well, it's about all of the middleware that goes between the digital twin and the hardware. And some of the sort of discussion that we want to have here is about looking at development and test of systems. And so you think about sort of typical systems development. You go through, design, build, test, into simulate, into living lab, and then you have this sort of learn loop that you come back on. And one of the roles for simulation here is about speeding up development. It's about providing robustness and resilience. It's about looking at how we collect data for doing offline learning, how we do things like enable online teleoperation. And there's all sorts of things to do with distributed development. As we've seen during the pandemic, there's interesting challenges in how do you get people to design, build and test robotic systems in semi-realistic environments, or do teleoperations in real living lab environments when people can't physically be there. How do you do that? So there's a whole discussion that we're going to look at here. So some of the idea with this physical fabric is to think about how we can do things like define standards, how we can think about middleware, and how we can think about having shared open data standards that the robotics community can buy into. At the moment, lots of things are stovepiped, or things sit within companies, which means that essentially there's a lot of replication of effort that goes into the standard elements that feed into a robotic system. Taking information in, looking at point clouds, looking at how you resolve that out against a digital twin, and how you communicate down through middleware onto your robotic systems. And so there's an interesting discussion to be had about standards and about how you could essentially develop a national fabric that everybody can buy into, in the same sort of way as you see with things like Linux, where people share information because it benefits everybody as a whole. But within that, there's interesting opportunities for new business models that go into that. For example, the sort of buying and sharing of individual blocks, which are your secret source. You don't deliver, you don't tell people what's in those blocks, but you can buy and sell and share those different ways of operating. So, Ivan, if you go to the next slide. An example of this is things like universal connectors. This is one of the key pieces of work that I'm keen to try and push in this challenge. If you think about the ways that robots interface with other systems, for example, for getting power or for getting data, then we have things like 3-pin plugs in USB, which are well-defined standards that have been developed for specific use cases. And it's an interesting thing in robotics, which is that each robot has its own specific way of interfacing with, charging. It might interface with data in a particular way, but there's no universal standards with this. And universal open standards will open up all sorts of interesting opportunities for collaboration between companies and for ways in which you can do things like the co-design of novel robotic systems with new pieces of infrastructure. So if we take one of the narratives that we've been looking at in ORCA, which is about resident systems, fast forward to 10, 15 years in the future, are robots going to be involved in the sort of operations, maintenance, inspection, repair of public infrastructure? I think everyone would agree the answer is yes. And so some of this is about that, looking at connectors that will provide mechanical connection, power connection, data connections, as a way of basically facilitating that conversation about standards and modularity. If we go to the last slide, Ivan, one of the things that we're going to do within this current phase of the ORCA Hub is to look at modularity, to look at how we can embed some of these universal connectors with design affordances to facilitate this conversation about general purpose robots and modules and how do people work with one another when they work remotely. So the idea with this specific task is to look at how you would design a new type of robot system where everything is going to be done remotely. People are going to be collaborating using this digital fabric to develop a system that's well designed to a number of different standards that then feeds into best practice for middleware and for how this sort of sim to wheel gap can be built up. And the end point of this will be something which interfaces back with a connector. And this builds on lots of work that we've been doing recently with some of our industrial partners who look at industrial robots, who look at general purpose robots, and who look at modularity. And just trying to facilitate that discussion of, within the ORCA Hub, we essentially have a small version of the overall macro system. And so let's have a look at how we can think about best practice within this specific task. So that's where we're up to with challenge 5.
Thank you very much. So we're moving on to how you can engage with us, and David Wavell will present this.
Thanks, Ivan. Good morning, everybody. For those of you who don't know me, my name is David Wavell. I'm the business development lead for the ORCA Hub project. So my role within the project is to be the industry academic point of contact for those companies who want to engage with us. So we have 3 engagement sessions for the next phase of ORCA, the first of which you're attending today, this webinar. So while today you've heard briefly from each of the challenge leads, what we'll do next is a bit of a deep dive into each of those challenges so that you can find out a bit more information about each of those challenges and how they may relate to your own business. And it'll also give you an opportunity to ask the lead academics some questions about what their plans are and what they're working on. So we'll be hosting these challenge-focused information sessions. We'll have one every day from the week beginning the 5th of July. So they'll be in the morning. Following those information sessions, if you're still interested in engaging and being involved, is what we'll do is we'll set up a series of what we're calling AIM days. So these AIM days are an opportunity for organizations to have one-to-one engagement with the researchers on specific challenges that you may have as a company relating to the work that we've just discussed today, and we'll provide more detail on during the information sessions. Ahead of those one-to-one engagement sessions, we'll be asking for a brief description of what the problem is, what it is that you would like to work with us on. That gives us some information to evaluate ahead of the one-to-one engagements. The date for these AIM days is still to follow. We'll also be providing a pro forma for these for you to send your descriptions over to us ahead of the session. So if you're interested in attending the follow-on sessions, either the information sessions or the Aims Day, please don't hesitate to get in touch with me. You can see my email address at the top right hand of the slide there. So thank you very much. I'll hand back over to Ivan, I think.
Thank you very much, David. So what's really, I think, clear to me out of what we've just presented today is the strength of the consortium and the strength of the collaboration. So ORCA has got 1 year to go, but we're really looking forward to keep the collaboration going beyond the funded ORCA project. One of the ways we'd like to do this is through the National Robotarium. So National Robotarium is a new national center for working at the interface between academia and industry. And it will be based in Area 12, but I see it as a national center, i.e. a place where industry can come and will build consortium of the best academics and SMEs around the country to solve the problems that you're proposing. And that's very similar to what we've been doing in the ORCA Hub. And so I expect that post-ORCA, we should still be able to provide the industry with the same type of service that we've been providing with ORCA. And the model we will have in this case is really that we'd like end users, you industry, to come to us with use cases, but also research priorities, area where you think more research must be done. And around National Robotarium, we're hoping to build an ecosystem of SMEs, but also research partners in the very same way we've done it with ORCA. So we can build a project team that delivers user-inspired research programs, which are then validating in living labs. And these living labs could be in Area 12, but also in other universities. And that finally we get to a more productization program with the help of the partners, SMEs, and the universities. And we would hope to co-fund some of this development through third-party support from government and other sources. So that's the model. And in a way, I could have put ORCA in the middle. That's what we'd like ORCA to become at the end of the funding. And we really need the support of industry to make that happen. Thank you very much, everyone, for attending. Thank you, everyone, for presenting. I hope that gave you a good idea about what we're doing, what we've done, and what we plan to do, and give you the appetite to engage with us over the next weeks on the engagement mechanism that David has highlighted.